My name is Carlos Arilla, and I work as a product marketing here in Genswan. About me, well, this is my three little helpers that help me with debugging the Kubernetes clusters sometimes. And I have a lot of hobbies like music, video games, sports, and so on. I have my first computer at 4 years old. It was a Spectrum 48K. It was actually my brother's, but I could use it anyway. And so that's when I started to like computers and all these kind of things. And basically, I've had computers all my life since then. Amstrad 128K. My first PC was an IBM PS1, which was a 3HS processor with the astounding amount of 40 megabytes of disk space and 4 megabytes of RAM. It was incredible. So then I studied communications engineering, and I've been working in IT for the last 15 years almost. And I've done everything from systems, integration, programming, and recently I started to do DevOps, which is the natural next step from systems. And I've been working in Kubernetes for the last 4 years, 5 years almost. And now I'm here at Giant Swan, very happy to be here. And let's see what we are talking today. First, I'll introduce a little bit ARM processors. I don't know if you are very familiar with them, but you all have used them like a lot, even when you don't know. All the advantages that they provide against other architectures like x86. And then we will talk about Kubernetes in ARM processors. And then after we have the Kubernetes cluster running, we will need to talk about applications, because that's the important thing. Kubernetes is nothing without applications running on top of it. And then we'll have time for questions and a little bit of chat. Okay, I'll leave here some things that happened in 1985. I will leave to you if they are good or bad. Okay, so Norway won Eurovision Song Contest. Congratulations, Norway. The Goonies, Highlander, and Back to the Future premiere. Super nice movies. Spain, which is where I'm from, joins the European Economic Council. No, European Economic. Well, okay. What is now EU? And Nintendo launches Super Mario Bros. Nice game. And then Microsoft launches the first Windows 1.0. And that year, Acorn creates the first ARM processor. The first ARM processor was not really a processor, was more like a coprocessor that was designed to help another processor with some task, but then was developed as a standalone processor. ARM processors had from the first version, which is this one that we can see here, has several versions throughout the years with different architectures and different degrees of technology. We can see here ARM v3, which is from the 90s. We can see the one, I would say probably the most famous ARM computer, which is Raspberry Pi. This is the first one that was about 10 years old. And that was a great impact because it made computing affordable for everyone. One of the greatest successes of Apple iPhone, the first iPhone had this ARM processor too, and the latest iPhone has one too, different version, more advanced, but it's the same. And now, recently, we've started to see ARM processors in personal computers for professional and personal use, like the M1, M2 series from Apple, which have pushed forward a lot the use of ARM processors in at home. But now we are seeing a lot of development in ARM processors in data centers too, and especially in cloud platforms. They are pushing hard, like AWS with Graviton, Azure, Oracle Cloud. All the providers have their own version of ARM machines, which you can deploy easily. So you don't need to use Raspberry Pi for your own ARM processing power. So it's ARM is not new. You've seen that it has more like almost 40 years, and it has been developed in parallel with other architectures like CISC or x86 architecture, and has a very good niche of market. All of you have a mobile phone, and probably, well, there were some phones with x86 processor, but it's really it didn't get any traction. So all of you probably have ARM processors in your pocket, in your phone, and your tablet, in the TV, and in your device, in your set-top box that you have at home. The main features of the ARM processor is that they are a RISC architecture. In fact, ARM means advanced RISC machines. So it's in the name. One of the advantages of the RISC architecture is the power efficiency. So it's interesting for mobility or data centers that have a lot of power usage. So it reduces the power needed to run the data center. These processors are multi-purpose. This means they can be used for anything, as the x86 architecture. But the main feature that has ARM processor is that they design different cores optimized for different tasks and usage. We have been this recently too in the x86 architecture, but it wasn't common until recently. But in ARM, it has always been like this. We have different cores with different level of power and efficiency, and we can combine these cores to create different processors. And the performance is comparable to x86, depending on the benchmark you see. If you see Apple benchmark, they say that no, this processor works like 3 times better than x86 processor. Well, you need to take that with a pinch of salt. But yeah, the performance is comparable. They are not less powerful. They all has all people believe that ARM processors were less powerful than ARM processor, but that's not true anymore. And one of the things that made this processor very popular was the licensing that ARM decided to use with this architecture. They created the cores, and you can license, buy the right to use this core, the design that is the silicon design, and you can combine them with some reference designs to create your own custom CPU. This makes very good this for phones or whatever, where you can combine these cores in different configurations with more power cores or more efficiency cores. You can create many things around them, like coprocessor or chips for AI or things like that. So every integrator can create their own SoC, and this makes very successful the platform, because if you buy an x86 processor, you need to buy the processor and then use it. But you can create your custom SoC, which allow you to do a lot of things. So basically, we have two advantages. First is the power efficiency. So the performance per watt in ARM processor is way better than x86 processor, and they're usually cheaper. Sometimes because of the lower cost or of the licensing mode, but sometimes too because the RISC architecture is less complex, so they are more easier to manufacture, so they are cheaper. Okay, now we know how Kubernetes, how ARM processor are positioned in the market and the things that they do and the history. Let's see how we can run Kubernetes on them, which is the main thing here. Okay, let's see a famous quote. With 4 raspberries, I deploy a Kubernetes cluster. It's easy as pie. Okay, you see here with databasing. Okay, so Kubernetes, many of you will say, what's this? I have Kubernetes running already in 4 Raspberry Pis at home. I installed micro Kubernetes or K3s like in 15 minutes. And I had Kubernetes and I was running pods and I was doing things with it. So do we need 45 minutes of talk to talk about this? Maybe no. So yeah, thank you for listening. Any question? Okay, bye. Wait. No. Wait. Sometimes when you talk about Kubernetes, you see these 4 Raspberry Pi with K3s, but now we are talking about real Kubernetes. And what I mean with real Kubernetes is something that is ready for production, for deploying real applications that do real stuff, not just, no, I will deploy my Home Assistant or my Grafana dashboard at home. So when you see Kubernetes, you see only the control plane, the nodes, and the pods running, but I see this, okay? I see all the applications that you need to run proper software here. And first of all, you need security, you need Falco, you need Kyberno, you need monitoring like Prometheus, Grafana, and other applications. You need to manage all your certificates. You need a way to deploy things like Flux or Argo or whatever. You need networking, cross-plane to deploy things. Networking, you need Cilium or Kong or Nginx Ingress to create all your rules to access your content. So there is like hundreds of applications running on top of Kubernetes that will make your cluster suitable for production. So if you try to run all these in ARM clusters, is when the thing gets interesting, because Kubernetes itself is probably easy to run, but when you start to run applications, what happens with crossplane? Will crossplane work properly with ARM processors? Will Cilium work? Will Istio work? With all these applications that you can see here, like Instana, Envoy, Sysdig, Sneak, all these applications work there? Let's see. So when you are trying to move your applications into a Kubernetes ARM cluster, there are different strategies that you can follow in order to migrate from your x86 clusters to your now ARM clusters. The degree of efficiency and cost that you can gain is different depending on the number of ARM machines that you can get. But there will be some requirements that will need to get x86 machines. So let's see 3 different strategies that we can follow and see what are the advantages and disadvantages of them and when these strategies are recommended. So the first one is we left the Kubernetes control plane in x86 and use only ARM machines. This could apply to manage Kubernetes like EKS, GKE, things like that, because you don't see the control plane, you can't control the control plane. So basically, control plane is something that is abstracted. It's probably running in x86 machines, but you don't need to get into that. Then we have a full ARM, which is everything's running ARM processors. and control plane, everything, applications, everything runs in ARM processor. So in the first case, you have ARM worker nodes. I've seen there's some problem with the order of slides, but I think it's fine. So the best thing in I don't think this is fine. Okay, let's talk about this. The main issue we have here is that we have two different kinds of nodes. And if we want to run, for example, diamond sets that need to run in all the nodes, worker nodes and control plane nodes, it might have a problem if we don't have applications ready to run in both. So we need ARM image, we need x86 image to run in both. Good thing is that if we are deploying clusters with a software or with a CI/CD that we already have in place, this is probably easier because we don't need to change that to deploy all the control plane. Control plane keeps deploying like it was before. We don't need to change that. We only need to create these ARM node clusters, and these are node pools, and deploy applications there. The good thing is that we are still improving the efficiency, but not by much because we still have all the control plane nodes in x86. When we are using this, we want to use ARM, but we don't want to change a lot how we are deploying my clusters. So I need to keep this running, and I only change some nodes. When I need to use this too, when all my applications are ready to run in ARM clusters, ARM nodes. So everything that I create, everything that my software, it's going to work on ARM. If I go from ARM, okay, everything is ARM. So the control plane is ARM, all the worker nodes are equal, so daemon sets are fine because all the nodes are equal, and I get the maximum power efficiency and cost efficiency, of course. But then we need ARM images for everything, and everything is everything. Control plane, everything related to Kubernetes, everything networking, everything needs to have ARM image. And we might need to build and maintain some images that are not available for ARM. Usually Kubernetes control plane and applications are Kubernetes itself. It's ready to work on ARM. But when we talk about Istio, Thilium, things like that, there might be applications that are not ready, and we will need to, they work, but we do need to build the images that we need to use. And one of the main things I see here is that all the control plane components work in ARM, but they have been tested much less. I mean, there are a lot of people running Kubernetes in x86 machines for a long time, and we've been testing everything. We have detected a lot of bugs, things that don't work properly, performance improvements, but this hasn't happened in ARM. So we might find unexpected bugs, unexpected bottlenecks, or things that don't work as expected and nobody has detected. So we might find some problems in the future. Never know. So this is the strategy to follow if you are starting fresh, for example, and you want to go ARM. This is the strategy. You go full ARM and you forget about x86. I want to change my cluster creation, so I want the maximum efficiency. I'm willing to change how I create those clusters, so I don't care. So this is the I want everything ARM. Is the most ambitious plan, but if you are starting from scratch, this is probably a very good way to start because it's much cheaper and power efficiency, and you won't need to maintain like 2 pipelines of everything for using ARM images. And then you can mix worker nodes too. You will have node pools which run ARM machines, node pools that are x86 machines, and the control plane can be ARM or x86 depending on your necessities or your CI/CD or however you want to run it. The main thing that we have is that we can decide which control plane is best for us. So if I have already up in place a CI/CD that is deploying my clusters and maintaining them, maybe I don't want to change it and I will stay with x86. I don't know. And the main thing is that sometimes we will have applications that won't work on ARM processors. And this way, it's an easy way to run these applications because you can run applications in the x86 nodes, and the applications that are fine can be run in ARM nodes. The same issue that the first one, we have mixed nodes, so daemon sets could be a problem potentially if we cannot run both images. We will need multi-arc images that are bigger in size. And we don't know the exact performance of our applications in ARM and x86, so we might need different limits and requests for all the applications in the different nodes. This could be a problem potentially. And then we need to manage what runs in which node, which is something that Kubernetes has a lot of mechanism for it, but it complicates everything. Like you can create node affinity, so one specific application is always deployed in some kind of nodes. You can create taints and tolerations. There is a lot of ways to do that, but it complicates because all this information needs to be in the deployments or in the stateful sets that you create in all the workloads. So it complicates everything, and it needs to be have an account when you are managing all this. And of course, if you run less ARM nodes, you are gaining less efficiency, less cost effective, but you will still be improving somehow. So I will use this when I need to run some applications that are not feasible in ARM. They don't work in ARM processor. But I want ARM because I need to improve efficiency. So this might be a good strategy. Let's see if there is any question. I've never used ARM machines. What is the best configuration to start? If you have never used ARM machines, I would probably try running the x86 control plane with ARM node pools in some cluster and try it. Does it make sense to migrate to ARM if I have already several clusters in production? Well, yes. You need to take care of the applications running there. So if your applications are ready to run in ARM clusters, you can migrate very easily. You can start creating pools of ARM nodes in the cluster that you already have and start trying. And the migration don't need to be like aggressive. You can gradually migrate loads from x86 nodes to ARM and finally go to full ARM clusters if you need it. The typical cost saving full x86 versus full ARM. It depends on the nodes that you are using and the loads. It can be up to 50% of saving. The numbers will vary a lot depending on your application, on the things you are running, the size of your cluster, and so on. But that's a a good target, like I'm saving half of the cost and the power. I would say between 20 and 50 would be a good number. Okay, so let's talk about your applications. Now we have our cluster running with one or the other alternatives that I suggested. But now the applications that you are creating in your development teams need to be migrated to ARM2. So this process is different depending on your application, and it can be from very easy to not easy at all. But it's important to have in mind that, okay, we are saving money, we are saving power from the clusters, like running the cluster will be cheaper, running the cluster will use less energy, so it will be greener, we will be emitting less CO2. But we need to have in mind that we might increase the cost of the application development and the application deployment, all the CI/CD cost. And we might use more power to create these CI/CD pipelines and to test everything. So we need to be sure that we are not offsetting one with another and that the net gain will be in our favor. Okay, that's the missing slide before. So development process, I divided in three main steps, like compilation. The apps need to be compiled for ARM processor. Compilation is a generic term. I know that many languages don't need to be compiled, but I mean, you need to be sure that your application runs in ARM processors, even when you are not creating Docker images or containers, but the application needs to run. If you are emulating x86 in ARM processor, probably this process is not for you. You need to run natively in ARM to be able to get advantage of these savings. Then you have the CI/CD structure, the pipelines. What do you need to take this program that is already compiled or working and take it to the cluster? All you need to do, like testing, you need deploy tools, you need all the things that will allow you to finally get this program running in the cluster. And then you have the image registry. That is the place where you are storing your images. Most of the modern registries support multi-arch, but you need to be sure that the registry that you are using supports it, because sometimes old versions don't work properly with multi-arch images. So let's see how compiling for ARM works. Any language is different, so there's no general rule here. But for example, you can probably compile most of the C or C++ or these compiled languages for ARM. There are a lot of tool chains for cross compilation. So basically, you can finish with a binary that you can run in ARM processors that will probably run very well. Other languages like Java or interpreted, they need the virtual machine or the JVM or the interpreter or the piece of software that runs this code and converts it to machine code so the processor can run it. Most of these languages have already this piece of software working for ARM processors because basically mobile phones, tablets, and there are a lot of things that work with these languages. So it's pretty easy to have this version. You only need to check that it supports all the features you are using and that all the libraries and everything that you are using. CD pipelines is where the start gets more complicated, or not more complicated, but where the cost starts to escalate if you are not doing things well. First, you need to build your images. And build for ARM is not difficult, but it's not immediate. There are tools that, like Docker BuildX, that can build multi-arc images without having these ARM machines. But there are other ways, like creating ARM nodes only to build these images and so on. Then you have to test, because we all know that we test everything before deploying to production, right? Right? So we need to test only x86? No, we need to test x86 and we need to test ARM machines, because they can have different nuances that might be different. So we have to test everything. So sometimes you need to double your test infrastructure. So you need to perform tests in these different architectures, usually at the same time, and that involves probably creating more machines. So then we start to offset the savings that we are doing in the cluster itself. So we need to be sure that this makes sense. And deploy. Can you deploy it? You need to prepare probably the manifest if you need to ensure that the architecture is honor and that you are properly setting it. Do you might need to have some mechanism to know where to deploy what, like node affinity, taints and toleration. And when you start, Kubernetes is like a rabbit hole that when you do a hello world, it's very easy. But when you start going through the rabbit hole, things get complicated. And when you start working with taints and toleration and this kind of advanced configurations, things can get tricky. One example of this, for example, is if you are using GitHub Actions. Do you know how to run ARM machines in GitHub Actions? That things get complicated. GitHub Action, for example, doesn't allow you to run ARM machines. You need to run like virtualized ARM machines, which are very, very slow. So you could have to have that in mind. And there are some providers that provide ARM machines that you can integrate with GitHub Action, for example. So these are the things you need to research in order to make these pipelines and this process suitable to work for. This requires work, this requires time, this requires investment. So you need to be sure that everything makes sense for you. And then the registry. Most of the modern registries, like Harbor, Docker registry, support multi-arc. Okay, you need to have in mind that multi-arc images are bigger than single arc images. Usually they are not like twice as much because they share some layers and things like that, but they are considerably bigger. So we need more space in the registry. We might have issues if we don't have enough space. And we have seen in the past how some registries, especially older versions, don't honor the architecture label. You say, okay, give me this image, ARM architecture, and the registry just return the x86 image. Like, I don't care. So you need to be sure that the registry you are using is honoring this multi-arc. Usually all the registries that are managed by the usual cloud providers work fine with this, but it's something you need to check first and report or change the registry if it doesn't work. So this is another thing. So you are stacking a lot of things that you need to check, like, can my code run? How do I do my pipelines? So you will need to research a lot of things. The other day I read a post. I don't know if you know Alex Ellis, that did a lot of work about functions as a service in Kubernetes, and he had a blog post about running ARM machines in GitHub Action. So you can check it in Google. You will probably find it useful. So main takeaway from all the research I did and the test I did with ARM cluster is that the cost saving and power efficiency can be really important, like up to 50%, which is a lot. That is like an ideal value. I know that probably about 20 or 25% is more realistic, but even that is good value. If you are running clusters from, I don't know, 100 machines, imagine saving 25%, it's a lot. And Kubernetes in ARM is not easy if you are having in account all the things surrounding Kubernetes, like security, monitoring, networking, and so on. So you need to have in mind that things could get complicated, and debug Kubernetes, as you know, is not always easy. And then you need to check that everything you are doing, like the software you are programming, is working on ARM. And this is not trivial sometimes. Sometimes it is, depending on your application, but there could be a pinpoint here. And then you will probably, if you are running now in x86 and you want to migrate to ARM, you are maintaining duplicated pipelines. And this can be complex. This can be expensive. So the migration process needs to be planned accordingly. So the time, if you are going full ARM, it's like go fast, because maintaining all these duplicated things is expensive. So this can offset a little bit the efficiency that you are winning in the cluster itself.